This is called a chi-square, and it's written this way. I want it quiet. And we write it with this X, like this. Chi-square. It deals with the variance and the standard deviation. Whenever you guys are ready, we'll get started. All right. The variance and the standard deviation. If you remember back to your last test, the last question I gave you had a standard deviation of 0.01. And I asked you to do a confidence interval and to tell me if it went up or what happened between the 95 and the 99%. Now, if you didn't round out to 4 decimals and you only rounded to 3, you told me they were exactly the same. But the standard deviation was very small, and some of you commented the standard deviation is small, 0.01, which made your confidence interval be really, really close if you didn't go too far out. Now, we have to find a way to measure variances and standard deviations. For variance and standard deviation, things that are used for this are things that are measured small. For instance, if you're looking at like the size of a boat, you know, a boat that has to fit into, say, your watch. I worked at a watch factory when I was in college in the summer. And we put these little tiny screws into the watch faces to hold the pieces together. It was a horrible job, but it was a college summer job, so we knew what we had to do. But the size of the screws were so tiny. Now, they're small enough. Imagine measuring a variance from them. You have to make it so that it fits perfectly, it doesn't fall out, and if you are a little bit off, it's not going to fit into where it needs to go. So that's something we use variance for, something that has a very small measurement. A lot of manufacturing uses variance in things, and we need to do the same thing with the variance and the standard deviations as we do with your mean and your proportions. Now, we start the same way. Population sample. We did the mu for your population mean. We did the x bar for your sample mean. We did the p for your population proportion. The p hat for your sample. Do the same thing with your variance. This is your population variance. This is your sample variance. This is your standard deviation for your population. This is your standard deviation for your sample. These guys are called, the same as those were, your point estimates. We need to use your sample to estimate and come up with an interval that we can see where your population should fall. Again, a confidence interval says how confident you want to be that that population will fall between there. And in this case, we'll be using your sample standard deviation and your sample variance. Now, these unfortunately do not have a calculator step. They're kind of a little bit involved with the formulas. I give you the formulas, so all you really have to do is find the pieces to fit into it. And we're going to do that together on this. So if you kind of just like walk through this with me, we'll get into how we do this. So we know the point estimate. Now, your chi-square also works very different than your normal curve. Your normal curve up to now did this. With your mean in the middle, your negatives, your positives, your standard deviations, right? Your chi-square works very differently. Your chi-square is all in a positive quadrant. It goes like this, only this quadrant. It doesn't go across to the negative. And it makes a series of curves. And your book probably has a nicer design. However, these series of curves are based on your degrees of freedom. Remember how we found your degrees of freedom for your t? We took n minus 1. We're going to do the same thing for degrees of freedom in here. same degrees of freedom. Everybody gets a choice except that last person. So n minus 1 on your degrees of freedom. Now, when we get through this, notice these curves. They all start only in quadrant 1, which means they're going from 0 to infinity. There's no negative numbers here. Like your z-scores had negatives and positives, your t's had negatives and positives. Your chi-square values have no negatives in them. They go from 0 and on up. As your curve degrees of freedom increases, you get closer and closer to your normal curve. It'll model a normal curve a little bit better. But we'll still use any n, and we'll still find our degrees of freedom. And we're going to be using a different table to find these values in here. So as we walk through this, try to remember that inside the curve now goes from 0 to infinity. And, not to confuse you even more, but when we did your z-scores and your t-scores, your area was always to the left of your z-scores and your t-scores. Your chi-square is different. Your area is to the right of the critical value. It's to the right. Now, if you look at your, I forgot to print you out a copy of the table, and I will do it today. If you look at your blue binder part, the little blue margin, go to A19. A19 is the table 6, and I'll print one out for you today. But A19 is the table for your chi-square. Notice the graphs on the top. See where they show you the area to the right? Your area goes to the right, not to the left. This is very different than your Z and your T. And when we do a two-tailed, we're going to deal with the two-tailed kind of similar to it on the two-tailed. A19, it's where your blue binder is in the back, your blue edges. That's table 6. We use that table for your chi-square. Notice the values inside, they're all positives. All positives. And we only have positive numbers. And I want you to notice on your table, look at the exactly in the middle. Do you see exactly in the middle? You'll see 0.90, 0.10. You'll see 0.95, 0.05. It's symmetric, like this. See the symmetry through the middle of the table? When we do one of these, we're also going to do the other one. We're going to find its matching pair. So the table's not so bad to use, but there is no calculator step for this. So you do have to use the formulas, and you're going to have to use the table. But the table's not so bad. It does work differently than your other two tables do, just so that you know that it does. Okay? Chi-square has a nice little formula. This is not the same as x squared. It's written like this. It's kind of a squiggly line and a straight line through it. That's your chi-square symbol. Okay? Here's your chi-square formula. Again, this is the population variance. This is the sample variance. So if they gave you a population standard deviation, you would then have to square it to get the variance. Because remember, we always find the variance and then we took the square root to find the standard deviation. So you have to kind of have a little opposite approach. So here are some of their characteristics. All chi-square values are greater than or equal to 0. And so there's no negatives. They go from 0 to infinity. You're in quadrant 1, from 0 to infinity. No negatives. I think I put this on your note page. The chi-square distribution is a family of curves determined by the degrees of freedom. Again, we're using your degrees of freedom. And you can see on your chart, the left-hand column on your chart on A19 says degrees of freedom. That kind of helps you see what you're supposed to put in there. Degrees of freedom is your sample size minus 1. The area under the curve of each chi-square distribution, no matter where it is, no matter what size it is equal to 1. That is the same as your z-score. Remember your z-score? The whole area was equal to 1. Well, your chi-squares, no matter what these look like, no matter what they look like, they're all equal to 1. And they're positively skewed. Their tail goes to the right. Their tail is to the right. The higher is to the left, and they come out like this. Excuse me. They're positively skewed to the right. Do you have to know that part of it? No, but you should know that it's equal to 1. You need to know this, and you need to remember that they're always positive. They're always in, like, quadrant 1, if you will. Okay? Once we get working with this, they seem a little strange, but it's not so bad. So now, we need to find, what we need to do when we work with your chi-square is we need to find 2 critical values for whatever level of confidence they give you. One on the right, one on the left. So we call it a chi-square R, and we call it a chi-square L. Now, it makes sense that the L would fall at the left, and the R would fall to the right. Now here again is where my graph comes from, right? So I find the left one, I find the right one. Remember I showed you symmetry in your chart? You're going to use that concept to find it. You're going to find the right one and the left one all the time. Your area is always to the right instead of to the left like on your z-score. You have 2 formulas for this. Your chi-square right tail says 1 minus your confidence. This is your confidence level. Like say it's 0.95, whatever it happens to be. And the other one is the plus. I'll give you those formulas, but when you look them up, the easiest way to do this is add 1, subtract 1, then divide by 2. When you find your values, because your numbers go from 0 to infinity, the smaller one always has to be the left value. The larger one is always going to be the right value. So you really kind of don't have to worry about how do I know which one is right or left, right? Because they're very similar. What you're going to have to do is find the 2 of them, and then we can look this up. Like say for instance, if my confidence interval is 0.95, I want you to be 95% confident that blah, blah, blah. So we put this in. We divide this by 2. We do this again, and we add this. So one of these comes out to be 0.975, and the other is the 1 minus thing. 1 minus this. Now, if you look at your table, on A19, just follow along with me on A19 for a second. Put your finger on 0.975 and put your finger on 0.025 and just kind of go down those columns. Notice those values are all positive. Which one would be your left one? The 0.975 or the 0.025? 0.975 because it's less, right? Did we have to remember that the left one was the plus? No. We can find it as soon as we find our pair. We're going to find a pair, and we're just going to remember that the smaller one has to go on the left because this goes from 0 to infinity. So you read your numbers left to right. So we don't really have to remember this part too much, which one goes where. We just have to remember 1 plus the confidence interval minus 2. And really, that's all you have to remember. Just find one of them, subtract it from 1, you find the other one. Because your chart is symmetrical about the middle. So even if you forget which one you're doing, you'll find the other one. That's not so bad. It's scary when we first look at this because you're like, how am I going to remember this? It does make sense as we go through it. You guys have any questions so far? Okay. All right. All right, so let's try one of these. Example 1. Keep track of your table in the back, too. Oh, well, actually, for this one, they give you a little example. We're on page 313. We need to find the critical values for the chi-squared R right and chi-squared L left, for a 90% confidence interval, when the sample size is 20. Now, it's going to work like this. It goes in here somewhere. We got a left, and somewhere here, we got a right. Okay. Which formula do you want to use? The one plus C over 2 or the one minus? Just pick one. Plus. Okay. 1 plus, this is my confidence interval. This gives me 1.90 divided by 2. So this gives me 0.95, right? Okay. I find the other one by this. So, these are the guys I'm looking up. Do you use the minus 1? This gives you 0.10 divided by 2. Oh, that gave me this one. Then I could do the 1 minus and find that one. Because your formula says 1 plus C divided by 2, 1 minus C divided by 2.
So you're going to use 20 in all though?
Oh, that's your sample size. That's going to give us our degrees of freedom. This guy's your n. So n minus 1 gives you degrees of freedom. Okay, so your degrees of freedom is 19. The columns on the top you have to look for are 0.95 and 0.05. Okay, yeah, they kind of highlight this for you. If you look at 313, I don't have it on my board, but if you look at it, see where they found 19 and 0.95 is 10.117. And follow across to 0.05, 30.144. Define those two according to their chart. Okay, everybody's on 313 with me? So, I still don't remember which one is left and right. So, of these two numbers, which one would be your left? The 10. Good. 10.117. And this guy, 30.144, is your right. So all you have to remember is degrees of freedom, and your table kind of says on top, degrees of freedom. And then you have to remember one of these, just one, and I will give you them. I'll give you those formulas. But would either one still give us the same result? Either one. So
For this one, it's not always like this one's plus and
yeah, the left is the plus, the right is the minus. Because the left,
the plus
oh yeah, it's kind of like a reverse look to it. So it's like that's why I say don't get hung up on which one goes where. Find them and then put the smaller one on the left hand side. Because to do that, to remember the plus, because remember area is to the right of this thing, not to the left. So it's an opposite way of thinking. Our area on this curve, guys, is to the right. So it's an opposite way of thinking. Okay, so you guys do try it yourself, number 1, at the bottom of 313. Alright, so we need to come up with a sketch. View to the right. It doesn't matter which way you know how you draw this. We've got a left, and we've got a right. So how'd you start this? Samantha, how did you start?
1 plus 0.95 divided by 2.
Okay, so Samantha decided to add this and divide by 2. And you got what?
0.975.
0.975. And then what did you do?
Subtract that from 1.
Good. She subtracted this from 1. She could have done the 1 minus 0.95, but why go through that when it says its complement? 0.025. These are the tops. This is what she needs to read from the top. Jerome, what did you do next? Claire, what did you do next?
I have a degree of freedom.
Okay, the only other thing on your chart says degrees of freedom. And you found that to be what? Good. 25 minus 1, 24. Now, all you guys have to do is look at table 6, come down to 24, read the .975, symmetric over here is .025, and take out these two values. Just take them out. Which one goes on the left-hand side, the smaller or the larger? The smaller. So, Alyssa, what'd you get for your smaller one? 12.401. Lizzie, what'd you get for your larger one? Okay. Taylor, what'd you get for your larger one?
39.364.
Okay. Is this what you guys got?
Yes.
Okay. Questions? Okay. Try not to get hung up on which formula goes where, because this curve works differently than your other ones. Area is to the right. Your curve starts at 0. There's no negatives. Just concentrate on one's going to be a plus, one's going to be a minus. It doesn't matter which one you do. The other one is its complement, 1 minus that, because your area under the curve is still 1. Okay, I'm going to give you some to do. So, page 316, 2, 4, and 6.